Okay. The presentation is called Beyond Hubble, and it mainly deals right at the beginning with the James Webb Space Telescope. Uh, Exciting times because after 3 years of delay and lots of cost overruns, but we won't talk about that. The Webb Space Telescope is actually going to be launched on December 18th. This presentation is mainly some videos, and then I'll talk through some of the the other factors surrounding the launch, and then what comes after the James Webb. So let me get into the presentation here. Oh, okay, back to the presentation. Okay. First of all, just a misconception here. The James Webb Space Telescope is not a replacement for the Hubble. A lot of people look at it as a replacement for the Hubble. The Hubble is not going away. Okay, the Hubble is and will continue to be a spectacularly successful space telescope. With, knock on wood, cross your fingers, send it good wishes and good hopes. It will continue to function for years to come. That's the plan. All right. It actually was out of service, I believe, last June. It came back into service in July using the backup computers. It's fully functional, but it's fully functional on basically all its backup systems at this point. Barring any real catastrophic failures, the Hubble will continue to function. Again, like I said, the hope is that it'll continue to function for years to come. As you can see by this graphic, there's very little overlap in the capabilities of the Hubble and the Webb Space Telescope. The Hubble sees light in the upper range of ultraviolet, the entire visible spectrum, and the very lower range of infrared, the near infrared range. The Webb telescope is fully infrared. Right. If you want to look at it one way, what the Webb telescope actually is a replacement of is the Spitzer telescope. All right. It does what the Spitzer telescope does, but with much higher resolution. All right. So there's no real. It's not a replace. Again, it's not a replacement of the Hubble. It works alongside the Hubble. All right, so that's kind of an important note. So let me go on. All right, there's really 3 parts to this presentation, and the first 2 parts are really videos. Okay, why? Why is the Webb telescope being launched? Why is it important? The second part of it is the how. How is it being launched? How does it get to where it's going to get? How is it going to start functioning once it gets there? And then what's next afterwards? What are we looking at? There's already another telescope on the drawing boards. Okay, the first video is called Seeing Beyond. Okay, the James Webb Space Telescope, and these are videos that are produced by this organization called STSCI, the Space Telescope Science Institute. It's a 14-minute video. I'd love to take credit for it, but smarter people than me produced it. So let me go ahead and start it.
Since the first astronomers pointed telescopes at the heavens, they have sought to see more, see farther, see deeper. Space astronomy changed on April 24, 1990, with the launch of the Space Shuttle Discovery, carrying aboard it the Hubble Space Telescope. A lot of people think we launched Hubble into space to put it closer to the stars, but the real reason lies in that old children's song, Twinkle, Twinkle, Little Star. We all know that song, and it describes a very real phenomenon. The Earth's atmosphere both distorts and blocks light coming in from space. In space, beyond the atmosphere, the stars shine steady, and that allows you to get the stunning images we've become accustomed to seeing from Hubble. But that wasn't Hubble's only benefit. It's also one of NASA's great observatories.
Sure, John. What's going on?
Getting an awful lot of static. So try a simple thing to see if you can mute your microphone.
Oh, yeah.
That works.
Yeah. Okay.
And then when the video is over, of course, just unmute yourself.
Okay.
And then hit continue.
Yeah, hang on. Hey, John, can you mute me?
I can, yes.
These are general-purpose telescopes designed to be able to observe anything and everything in the cosmos. There are a lot of observatories in space, but most of them are designed to answer one or two specific questions. Hubble was built to be as inclusive as possible. It was supposed to answer as many questions as you could think to ask, at least as far as its design allowed. And Hubble succeeded splendidly at that. We've seen planet-wide dust storms on Mars. We've seen the astonishingly strong and surprisingly variable auroras of Saturn. We've looked deep into dense star clusters containing tens of thousands to millions of stars. We've examined the birth of these clusters as they emerge from the interstellar clouds. And we've watched stars die, some releasing their outer layers gently into space like smoke rings. Others forming cosmic butterflies. Some expiring in tremendous explosions that blast their material across the cosmos, expanding for tens of thousands of light years until their remnants ultimately fade away. We've explored the varieties of galaxies, some with beautiful spiral shapes, and some with vast ellipsoidal collections of hundreds of billions of stars. And we've seen galaxies in massive clusters of thousands arrayed through space and time. This is perhaps the most important image Hubble has ever taken, the Hubble Ultra Deep Field. It shows us galaxies stretched all the way across the universe, 5, 6, 10 billion light years away. This is light that's taken billions of years to reach us in our corner of the universe. So we see these galaxies not as they are today, but as they were when the light left them, like getting a postcard in the mail that's been traveling for a very, very long time. And in the end, we see nothing. Is that because we've reached the end of the universe? No. What we've reached is the limit of Hubble's vision. As amazing as Hubble has been, we've come up against the immutable reality that Hubble can't, in fact, see everything. To carry us farther, to step beyond Hubble, we need the James Webb Space Telescope. Like Hubble, Webb is a general-purpose observatory. And like Hubble, Webb will orbit in space, giving it the clarity that comes from being beyond Earth's atmosphere. The Webb telescope sees infrared light, which is visible to the human eye, though we still perceive it as heat. Putting an infrared telescope like Webb in space is going to open entirely new regions of the universe to us. To understand this, you need a little astronomical background. You've probably all heard that our universe is expanding, but what you may not know is that as it expands, the light traveling through the universe also gets stretched. So what started out as visible light and ultraviolet light, the two types of light the earliest objects in the universe emitted most strongly, is changed. It's stretched into another wavelength, infrared light. If we want to see the earliest objects in the universe, we have to see that faint infrared glow. So why haven't we done this before? Well, we have. We launched the Spitzer Space Telescope, which isn't as well known as Hubble, but has made incredible discoveries of its own with the infrared capabilities Hubble lacks. But when it comes to resolution, Spitzer's images are a lot more like ground images than they are like Hubble images. To get Hubble quality images in infrared light, we need something more. We need a giant mirror. Spitzer's mirror is just over 2.5 feet across. Hubble's mirror is about 8 feet across, so that's about a bit taller than a human being. And Webb's mirror uses 18 hexagonal mirror segments to create a reflective surface more than 21 feet across, almost 2 stories tall. Clearly that's pretty big. How do we get something that size into space? Obviously we can't ship it like this. The answer is origami.
Hang on, we're having some
We're going to fold Webb up inside the rocket that launches it into orbit. Once it's in space, it starts to unfold. The massive mirror opens up. Its tennis court-sized sun shield, which will protect it from unwanted infrared emissions from the sun, Earth, and Moon, stretches out. And all this happens while it travels approximately 1 million miles away, to a point farther away from our planet than even the Moon. So, what are we going to get for all this effort? We are going to be able to see past all these galaxies in the Hubble Ultra Deep Field. We're going to be able to see beyond even the most distant red dots in these images, the tiny, newly formed galaxies at the very edges of Hubble's vision. We're going to see the most distant and earliest galaxies in the universe, the first stars and galaxies to form after the Big Bang. We call these objects the universe's first light. Hubble has been able to observe the adult, teenage, and child galaxies of the universe. Webb will see the toddlers and infants, filling in our story of galaxy formation and evolution as surely as adding missing photos into a family album reveals how humans grow and change over time. But this isn't the only area where we know Webb will provide breakthroughs. This is Hubble's image of the Eagle Nebula, the famous Pillars of Creation photo. Inside these pillars of gas and dust, new stars are forming, but we can't see them, because the dust blocks visible light. But it doesn't block infrared anywhere near as well. Infrared light can beam through the nebula, and if we can see it, we can see the newly formed stars within. Hubble's view of the Orion Nebula shows hundreds of newborn stars only a couple million years old. But if we zoom in on Spitzer's infrared image, we see thousands more hidden inside. Orion is the place where we get the best view of not just star formation, but also of the new solar systems forming around those stars. We know that planets, new Earths, new Saturns, new Jupiters are forming inside these dark dust rings, what we call interplanetary disks. But we can't see them. They're hidden behind the dust. Webb's infrared vision will allow us to see through these opaque clouds so we can discover how solar systems like our own came into being. we will be able to see what our own solar system would have looked like after the sun had formed, but before Earth existed. And Webb's vision is going to take us even farther than that, to individual planets beyond our solar system. This isn't one of Hubble's most dazzling images, but it is an important one. Several planets are orbiting around this star, but their light is lost in the bright glare of their sun. If we can remove the star's light, we can see the planets, these bright dots you see here. This is an infrared observation. Planets which don't shine with their own visible light are usually brightest in infrared. The best way to observe planets is with a high-resolution infrared space telescope. But Webb will be able to take even that another step further. Some extrasolar planets, from our point of view, pass in front of their stars. When that happens, some of the star's light passes through the planet's atmosphere. We can analyze that light and measure things about the atmosphere of that distant world. So what does that mean for us? Well, here is the plotted infrared light of 3 different planets. You're seeing the differences in those planets that indicate the presence of carbon dioxide, ozone, and water. These are the telltale differences between Venus, Mars, and Earth. The first signs of life elsewhere in the universe will not be photographs of civilizations or a visit by little green men. It will be features in the atmospheric spectrum of an extrasolar planet that show biological activity. And that's what Webb has the potential to give us, that tremendously exciting discovery. So when is all this going to happen? Webb is scheduled to launch in 2018, just 6 years away. An enormous amount of the work on the telescope has already been completed. All of Webb's 18 mirror segments have been ground, polished, coated, and tested. Its cameras and other instruments are nearing completion or in their final stages. But since Webb will be located 1 million miles away, it has to be perfect before it launches.
I take it you've noticed the video just stopped.
Yeah, it seems to stop when I go to the chat. So I'll refrain from going to the chat. Sorry, I'll start it up again. I'm not hearing any static on my end. Is it really bad when you're hearing it?
Yeah, but it sounds like if you're not hearing it, it's either a personal problem or something we can deal with later.
Okay. All right, I'll mute myself again and restart the video.
So we're testing everything. The pieces get tested separately, then together, then as part of the actual telescope. They're tested to make sure they work in the extremes of space and that they can survive the violence of launch. When it's time to test them as part of the entire telescope, they're brought to NASA's largest test chamber, this cavern-like thermal vacuum chamber at Johnson Space Center, which is being refitted especially for Webb. If it looks familiar, that's because it's famous for being used to test the Apollo space vehicles. It seems fitting that that chamber, used to prepare humanity for its first true exposure to the heavens, is also where NASA's next great space observatory is coming together. Every decade, astronomers conduct a survey to determine the astronomy community's top priorities. Webb is their #1 priority. This is the observatory they want above everything else. We've already explored some of the reasons why, but not the most important reason. If Hubble is any guide, Webb's most important contributions to our understanding of the universe will probably surprise us. Because it was designed as a general-purpose observatory, it is extremely versatile. The Webb Space Telescope will be able to answer the questions we have, and then move on to questions that we haven't yet thought to ask. For example, before Hubble, we thought the expansion of the universe was slowing down. But Hubble made crucial discoveries to confirm that actually it's speeding up, and for that to happen, there may exist some form of strange dark energy. This discovery won its scientists the Nobel Prize in Physics this year. The universe doesn't always work the way we think it does. it surprises us again and again. We've only begun to chip away at the mysteries that are out there. And Webb, because it's designed for this purpose, will be able to explore, confirm, or deny these discoveries as they arise. And that is the true power of Webb. Its potential for unbounded discovery, its ability to reveal wonders we didn't even know existed. That capability, perhaps more than anything else, makes Webb the future of space astronomy.
Okay.
I have no questions so far.
Okay, good. I've just one thing real quick. Oh, well, a couple of things really. That video was made in 2013. If anybody caught the reference to Webb launching in 2018 in the video, obviously that target was missed. It was it's because this is 2021. It's 3 years beyond the target for the launch date. The original cost estimate for Webb was 1.6 billion. On launch date in December, the overall cost will have exceeded 10 billion. So this is pretty well par for government work. But all that aside, it's a heck of a tool. If it meets the expectations, then it should be at least as exciting, at least as powerful a tool as Hubble was, and in orders of magnitude for what we can get out of it. This is what you're seeing here is a picture of the ultra deep field from Hubble. I just want to point out one thing: the square that's highlighted and brought out into the upper right corner here is the oldest galaxy yet discovered from this ultra deep field picture. Hang on, because I'm blocking part of my. I'm blocking part of the name for myself here. It's got this real catchy name of UDFJ 39546284. It's a galaxy that's 13.2 billion years old, which means that it formed when the universe was only about 480 million years old. As Hubble sees it, if you were to blow this, the UDF up to, to its full resolution, it would show up as a very faint red smudge, and then in the lower right-hand corner, it's blown up without color, and you can see that it just completely loses resolution. The hope for the Webb telescope is that using its higher resolution and using its infrared capabilities, it will bring that galaxy into actual, visible resolution. And not only that, there are in this UDF, there are spaces where nothing shows up. It's a very tiny space that was photographed. Within this very small space, there are 10,000 galaxies, but there are still black spaces where there's nothing. And the hope is that, or the expectation is that if when Webb photographs this same area, those black spaces will show galaxies that are older than this oldest galaxy. So there is a lot of expectation for Webb. So let me move on to the next video. The next video is shows the Webb Telescope deployment sequence. It's pretty interesting. It's a little shorter. It's 12 minutes, but it's really interesting how it goes out there. As people have probably heard, it's going to be parked in the L2 space, which is a point in space that's where spacecraft can be parked and they'll stay there. It's beyond, it's about 750,000 miles beyond the moon. But because of the combination of the Earth and the moon gravity and centrifugal force, it's once something gets parked there, it stays there. So it's a good place to put things. I don't know. I actually don't know if we have put anything out there, but at least the idea is that if we put the Webb telescope out there, it'll stay there. The bad thing about putting something out there, as opposed to the the Hubble, is, as you know, the Hubble, when it was first put into orbit, needed some repairs, and it's been repaired a few times. Because of the distance to the L2 spot, everything has to work first time, every time for the life of the Webb telescope. Repair missions are probably going to be nearly impossible. So it's a little, a lot of crossed fingers with this, but anyway, let me play the video. Just one thing before I started, the launch vehicle is an Ariane 5 rocket from the European Space Agency. The Ariane 5 is probably right now the most reliable launch vehicle, in existence. It's had at least 80 successful, flawless launches to date. So they're not taking any chances with it.
As the sun rises over the Guiana Space Center, the team conducts final checks on the health and status of the Ariane 5 rocket and its payload. The James Webb Space Telescope, NASA's #1 science priority. The Webb telescope is designed to look back to a time when stars and galaxies were first forming, over 13.5 billion years ago. With its revolutionary design and capabilities, the Webb telescope is about to unleash a new dawn of discovery.
À tous de vidéo, attention pour le décompte final. 10, 9, 8.
Seconds before liftoff, the Ariane 5's liquid-fueled engine comes to full power, followed by the ignition of the 2 solid rockets. We have liftoff. The Webb telescope is finally on its way, the result of years of study and development by thousands of team members in the United States, Canada, and Europe. Webb spacecraft ascends nearly vertically through the heavy lower atmosphere of Earth. As the rocket reaches maximum acceleration, the spent solid rocket motors are jettisoned safely into the Atlantic Ocean. Reaching the upper atmosphere where protection is no longer needed, the payload fairing is jettisoned and falls away. Accelerating through the atmosphere, the Ariane 5 rocket's first stage expends its fuel and shuts down. The empty first stage then separates from the upper stage. After first stage separation and before second stage ignition, the Webb telescope has a slightly downward trajectory as it speeds over the Atlantic Ocean. The upper stage motor ignites and the ascent to L2 resumes, never again to be interrupted. The exposed telescope is delicate and must be protected from the sun's fierce heat. To avoid overheating and damage, a carefully designed series of oscillations are performed that provide the necessary protection. Near the end of powered flight, the roll program stops and the launcher then assumes the proper attitude for separation. After separation from the Ariane upper stage, the Webb telescope continues its journey to L2 under its own power, taking the next step to its final orbital station 1 million miles from Earth. The Webb telescope is about to unleash a new dawn of discovery. The Webb telescope separates from the launcher's second stage. The white ring close to the Earth represents the Hubble Space Telescope's orbit, and the larger orbit is the geosynchronous orbit where most telecommunications satellites are located. The solar array is Webb's first deployment. When completed, all of Webb's electrical power needs are satisfied by the solar array for the remainder of the mission. The onboard control system continually monitors and updates the attitude to ensure power generation and thermal safety. To preserve the cleanliness of the mirrors, thrusters are located only on the sunlit side of the observatory. The trajectory is designed without employing a retrofire, which necessitates pointing the delicate telescope at the sun. If course corrections are needed, these velocity additions must be done early in the flight to most efficiently use the mission's limited precious fuel. After completing mid-course corrections, the Webb telescope passes the orbit of the Moon. Webb's initial transformation is the deployment of the sunshield pallets. The tower separating the telescope and instruments from the spacecraft and sunshield is next. Next, the aft flap deploys. This is key to managing momentum buildup and fuel consumption. This structure helps to balance the pressure from the sun's light on the Webb telescope around its center of mass. After the sunshield pallets reach their full positions, membrane launch restraints are released. These have kept the sunshield membrane safely in place from final stowage at the Northrop Grumman facility in California through shipment and launch. The sunshield protective covers roll back, permitting membrane deployment. The covers over the core region release next. Then the mid-booms extend and the sunshield assumes its hexagonal tennis court-sized shape. It is now time to tension the sunshield membranes, each thinner than a human hair, pulling each of the uniquely sized and shaped layers to their optimal position. When deployed, the sunshield allows the telescope to cool to 385 degrees Fahrenheit below zero, cold enough to liquefy air, while the layer closest to the sun is almost 190 degrees Fahrenheit above zero, nearly the boiling point of water. It's of almost 600 degrees. Truly fire and ice. Once in the shadow of the deployed sunshield, the telescope and instruments continue cooling down to their final operational cryogenic temperatures. At the completion of membrane tensioning, the secondary mirror deploys into position and is latched rigidly in place. The aft deployable radiator releases and springs into position, allowing the instruments to radiate their waste heat directly into space and away from the telescope. Disposing of excess heat is crucial to the mission so that it does not overwhelm the faint infrared signals to be collected from the cosmos. The cord-fold wings deploy and latch in place, completing the major deployments of the largest telescope in space. As the Webb telescope continues out to its operational orbit around the Sun-Earth L2, the observatory continues to cool down to its final cryogenic temperature state. A trajectory correction applied 29 days after launch puts the Webb telescope into its halo orbit, a key part of the mission design. The Sun-Earth L2 point is where Webb's orbit around the Sun is synchronized with Earth's. At this point, 1 million miles from Earth, Webb is free from the thermal influences of the Earth and all eclipses. Additionally, the Sun, Earth, and Moon, the brightest objects in the sky, are hidden by the deployed sunshield, giving Webb a dark, cold, and stable environment to carry out its mission of discovery. Once the mirrors and detectors are sufficiently cold, the wavefront sensing and control operations can begin. This sophisticated multi-step operation's ultimate goal is to position each of the Webb telescope's movable mirrors into their correct final positions and orientations. Once the mirrors are aligned, the mission team will continue checking out the science instruments, preparing them for operations. Commissioning is completed about 160 days after launch, and the science mission is ready to begin. This brings to fruition the work of the thousands of members of the Webb team from the United States of America, Canada, and Europe. Astronomers from all over the world can now use this facility to study the universe. NASA's James Webb Space Telescope is a game changer. Discoveries made by this observatory will rewrite textbooks, inspiring the next generation of future engineers and scientists. This revolutionary tool will provide an unprecedented view into the birth of the first stars and galaxies, unleashing a new dawn of discovery.
I have no questions in the chat.
Okay. All right. Let's see. What did I have to say about that video? Oh yeah, I thought it was interesting. It takes about 30 days for it, from launch to insertion to L2 to the final unfolding, and then another 130 days for calibration, checkout, it's a long process. They said it's, after launch, before, it's 160 days from launch to when Webb will be available for use. Long process. But I don't know, that was interesting. I have one more short video, which I thought was really interesting. It's Webb's field of regard, which the field of view of Webb, which I just thought this was kind of interesting. It's only a 2-minute video. So let me go ahead and start that.
Which parts of the sky can the Webb telescope see? The James Webb Space Telescope orbits the Sun in sync with Earth, but 1 million miles further out, beyond the Moon. The telescope's mirror is perpendicular to the 70-foot sun shield, which keeps it cool. The telescope's movement is limited in certain directions to keep the mirror and scientific instruments in the shade of the sun shield, blocked from the heat of the sun. But Webb can rotate to get a 360-degree view of the sky. As Webb orbits the Sun, different celestial objects enter its available field of view. Science observations with the telescope will be carefully scheduled to make the most effective use of Webb's time. Over the course of 6 months, Webb has access to the entire sky. Allowing astronomers to investigate a range of questions about how the universe works and our place in the cosmos.
That reminds me of the spirograph. You got room for a question now?
Sure.
Okay, this one comes from Jeff Masikian. That upon
Yep.
deployment, how long will it take for a single image to be captured and sent back? And will there be any video?
I don't know that. I don't know the answer to that. I can probably find that out. Video, I don't believe it does video. I think it's all still photography. The same as the Hubble.
I know that
same.
New Horizons took up to 12 hours and they were sent in bursts because they didn't have the antenna always facing Earth.
Yeah.
And with this thing as a spirograph, they'll probably use some similar technology of sending packets in bursts like
Yeah.
zip as well.
I think in the case of the Webb, the Earth, the antenna is mounted underneath the sunshade,
Mhm.
and it's pretty well always pointed towards the Earth. So I don't think you've got that limitation, unless there are times when the moon is in the way, between L2 and the Earth.
Well,
So
while you're researching it, let me give you my best prediction. It took
Okay.
12 hours for New Horizon will be around Pluto, and it takes 2 to 3 hours from Mars. I'm going to say it takes an hour or less.
Yeah.
So a
It's
million
not.
miles beyond the moon, and that's only like minutes away.
Yeah. It's not a long distance, when you're talking about light speed for communications.
Okay.
I don't believe it does video. But beyond that, I don't know. I don't know the answer to the question.
Right now, whoops. Another question that came in from Bethany is there an estimated lifespan for the Webb, or is it just go until it busts?
It's expected to last at least 20 years. But to 2040 is the expected lifespan. Having said that, we're well past the expected lifespan of the Hubble. So that 2040, with under optimal conditions may stretch out quite a bit beyond that. But the expected lifespan is 20 years.
Okay, that's good.
I don't know that if it was engineered correctly. The biggest danger to it is the sun. And right now, I think they've, the way it's been engineered, it's got a fair amount of protection from the sun. Barring, cosmic rocks, cosmic pebbles, cosmic dust. I think it's could be around for a long time.
Or maybe not work at all. I mean, there's so many moving.
There is that, it's like they said, it's we're sending up cosmic origami. Everything has to work right the first time. Everything has to unfold right the first time.
Yep. And it'll be worth the cost overrun. If it doesn't, a lot of people are going to be upset.
Yeah.
Given that the infrared wavelengths are much different size than visible and the near infrared that Hubble did, comparatively, with the mirror being much larger than Hubble's, what's the resolution going to be like? Comparably or vastly improved, or
it's going to be vastly improved. From what I've read, you can pretty well compare the the mirror size to the mirror size.
It bugs me that everything's compared to the Hubble when it really doesn't have anything to do with the Hubble. It should be compared to Spitzer.
Right. And you saw the side-by-side image of Hubble to Spitzer, but all they can really do right now is give an estimate of what the same image would look like with the Webb telescope. So it's hard to say really, but if you just look at the resolution of of the size of the mirror of Webb with Hubble, and look at it as aperture sizes, you've got a tremendous increase in size there. I don't know. I can't answer that question.
Yeah,
but like I said, there's a lot of expectation that the way that it was described is, some of the images, even within the solar system, where I picked these two videos up, and I give the link at the end of this presentation. Where I picked these videos up is a site, the website, the James Webb site.
Right.
The James Webb website has probably 200 different videos, if not double that. And a lot of them give specific examples of infrared targets, that the Webb will be looking at. Okay, where was I going with this? I had a specific reason for going. I'm getting old. What they're really planning on is, okay, here's where I was going with this. What the solar system targets in particular, because it'll be looking at everything. It'll be looking at targets within the solar system, deep space targets, and targets, as far away as you could possibly, at the limits of the known universe. Within the solar system, the kind of things that they were saying is the things that the Hubble sees or the Spitzer sees are things that then drive NASA to send probes to check out. Whereas the Webb, they won't be needing to send probes to check out because the Webb will have a resolution, sharp enough to see, to see on its own. They're expecting. There's at least one video there where they're expecting to see, to see Pluto in the same resolution that they did with the probe that went out there.
Horizons.
With New Horizons. So that's the kind of thing that they're expecting to get from the Webb telescope. Whether that's realistic or whether that's something that was written to get funding, who knows? Hopefully that's realistic. I mean, if all those expectations come true, this could be one heck of a tool.
Now, the questions that have come at me have led me to postulate one of my own. This may not be something you've researched at all, but visible wavelength we've broken up into many different spectra.
Yeah,
of course. And the Hubble is doing its own palette of sodium 2, oxygen 3, and hydrogen alpha.
Yeah.
I know the infrared spectrum part of the whole length of all spectra is of light, shall we say, is actually longer than the visible. Does it is it able to be broken up into various pieces that they could produce a color image, or is everything going to be black and white or false color red?
No, they can do color. There's actually one of the videos actually does that too. They can do color images. You can do the spectrum analysis. I mean, you've got that whole spectrum visible there too, or available there too. Because it's all there. You just need to, you can break it down. It's just in different wavelengths.
They won't be doing any of the visible light spectra. They'll only be doing
right.
all infrared.
Right. Webb doesn't see in visible light. It's purely infrared.
And infrared has wavelengths that can be separated out into different patterns, so they'll have color filters for them.
Yeah. I mean, you can see that in the Spitzer telescope too.
Okay, I've only seen Spitzer show one color, like red against a black background.
Oh, I didn't think that was true.
Okay,
I'm sorry. Maybe I'm wrong. I could be wrong about that. I actually don't know that much about the Spitzer, but I thought the Spitzer could also produce color images.
Hey, Chris, this is Bill.
Bill.
I'm thinking that the red-shifted targets that are going to be in the ancient space can be shifted to the right in order to provide some variations translated to our visible spectrum. So I think that's what Spitzer did. It's a translation kind of program. They just multiply or the wavelength into something that's appropriate to what our eyes can see. It's a false color, yes, but the red shift is all the way to the left. Multiply that out and you'll be able to see stuff in the visible spectrum.
Okay. I mean, there was that one slide there that it showed the or one piece of the video where it showed the different components of the atmosphere of an Earth-like planet. When it showed oxygen, carbon. It showed the Spitzer looking at an Earth-like, at the sunlight coming through the atmosphere of an Earth-like planet. So it's
And that's
got to
how
be
they
able,
know the spectra of the atmosphere.
right.
They,
So it's
they
got to,
subtract it from the stars spectra.
yeah, it's got to be able to do something like that.
Yep, that's what they do now.
Yeah.
So assuming the images from Webb will be stacked photons, if you will, except infrared photons to
Yeah.
make longer deep field,
Yeah.
not just have one single long exposure. They'll take a whole bunch of single long exposures and stack them.
I probably,
Well, it's going to be cool enough. They can certainly do it.
yeah,
And
yeah,
the detector's heat is probably the limiting factor, and being cooled to the point where air would be liquefied.
yeah, yeah,
It's pretty
super,
easy,
yeah,
safe to do.
yeah, yeah. It'll be super cold. This it's, you know, whatever temperature. I forget the exact temperature they mentioned, but yeah, yep,
Yep. Those were summations of some of the other two
Yeah.
parts of the questions I was getting.
yeah. All right, a couple more slides here. After the James Webb Space Telescope, what comes next? So in 2015, NASA worked with a group called Aura to define a vision for the next generation of optical space telescopes. Okay, so optical indicates that what they are looking at here now is in fact the successor to the Hubble. All right, they're not, where Webb is an infrared telescope. The one that we're looking for the vision for is an optical space telescope. The result was several designs, but with the top design being right now being called the HDST, the High Definition Space Telescope. If this ever comes to fruition, this name will probably change. You know, when the Webb Space Telescope was first accepted, it was actually called the Next Generation Space Telescope.
Yes, it was.
Yeah, so, you know, then this name will probably change. But right now, this is only on paper. No, you know, no two parts have been screwed together. There is no budget. The estimated cost is $10 billion, and the planned launch date of this non-existent telescope is 2030. I'm sure both that date and that number will change, but this is the telescope that right now is the planned successor to Hubble, and the planned whatever big brother to Webb. Okay, here is the proposed mirror, or the segmented mirror, if you will, for the HDST. You know, here's the single component mirror. Can you guys see my
Yes.
mouse? Okay.
Yes.
Here's the single component mirror for Hubble. Here's the 18 component mirror for the Webb. This would be the 36 component mirror for the HDST. Each component is actually bigger, larger than the Webb. Overall, it's 12 meters across. It's just a little bit less than twice the diameter on paper of the Webb. So it would have whatever, you know, if you work that out, I guess technically it's you know, at least 4 times the resolution of the Webb. These screenshots here are the estimated resolution differences between, you know, looking at a particular galaxy of the Hubble, the Webb, and the estimated resolution of the HDST, looking at the same galaxy. Do I have? Okay. The HDST is designed to again, this is all on paper, but it's designed to operate in the ultraviolet to near infrared range, a pretty wide range there. Near infrared, very little overlap with the Webb. It includes the complete visible light range. One of the advantages of that is, unlike the Webb, it would not need to be kept super cooled. So it's got that advantage. The sun shield, this is a picture of the mirror sitting on top of its sun shield. The sun shield would actually be thinner because it wouldn't need as much protection from the sun. And an interesting, I don't know how well this picture really illustrates it, but an interesting component of, hang on a second, interesting component of the proposal here is this thing floating out here called a star shade. One of the primary missions of the HDST would be to, with its incredibly high resolution here, would be to photograph exoplanets, high definition photographs of exoplanets. This star shade is a separate, separately orbiting object that's used to block the light from stars. I know this looks like a really bright thing. You could mistake it for the sun, but it's not our sun. It's actually a distant star with a planet orbiting it. So this star shade is about 80 to 100 meters in diameter, and it's floating separately anywhere from 160,000 to 200,000 kilometers away from the HDST. So it's this this separately controllable star shade that positions itself between the target star and the HDST, and basically just blocks that star. It's small enough where it blocks just the star, and any planets that are orbiting that star would be visible to the HDST. In theory, it's never actually been tested. There are plans to possibly orbit one of these things with the Hubble sometime in the next year or two to kind of test the concept to see how well it works. And if it works, then they may actually plan on sending multiple star shades up. With a single star shade, it could, with the distances involved, it could take weeks to move the star shade from one star to another. And the tolerances are very small. Having it be, I think they said having it be just a few yards or a few meters off target, would expose the star. It's an interesting concept anyway. So, if the funding goes through, and that's right now for NASA, that's a lot of money. If the funding goes through, then and if the target date stays, then they're talking about 2030 as a possible launch date. So here's some more information, and I'll send these pages out. Where I got those videos is this site here, webtelescope.org. Again, there's I don't know, there's at least, I think there's at least a half a dozen pages, and each page has at least, I don't know, 30, 40 videos. A lot of information. And then there's a couple of good articles here on the HDST, one from Sky and Telescope and one from Discover Magazine.